So let's say I want to solve an equation that happens to have a trigonometric function in it. And for an equation like this, what I'm trying to do is I want to find every single angle, x represents the angle, where the cosine function will give me a value of radical 3 over 2. Now think about the basic unit circle. There are actually two places on the unit circle where cosine gives you radical 3 over 2. There's one place in the first quadrant and there's one place in the fourth quadrant. So what I need is every single angle whose terminal edge points to one of these two directions. There's infinitely many of those, right? There's pi over 6 and all the coterminals to that angle. Those are the first quadrant angles. And also there's 11 pi over 6 and all the coterminal angles to that angle. Those are the quadrant 4 angles. Now I have a lot of freedom here in how I write the solution set. I can use indexing notation, and so I can write pi over 6 plus 2 pi k, or 11 pi over 6 plus 2 pi k, where k is any integer in the whole wide world. This is a very compact way of expressing the solution set. Alternately, if you saw that fourth quadrant angle and you thought that looked like negative pi over 6 instead of 11 pi over 6, you do get to write the solution set this way. These two sets actually do represent exactly the same set of real numbers. They're both perfectly valid. Let's say you didn't want to use indexing notation at all. Sometimes it's prettier or more useful to just use a giant list. And so in this case, you would want to substitute different values for k, like -1, 0, and 1, and generate different individual solutions to this equation. So for example, if I take this set right here, and I substitute k equals 0, I get pi over 6. If I substitute k equals 1, I get pi over 6 plus 2 pi k, or 13 pi over 6. If I were to substitute k equals -1, I get 11 pi over 6. So notice how every other solution corresponds to the first set. And over here, let's take this bottom one. If I were to substitute k equals 0, I get negative pi over 6. If I substitute k equals 1, minus pi over 6 plus 2 pi is 11 pi over 6. Every other solution here corresponds to the solution set. So this is the entire set. Please note it's not correct unless you have an ellipsis, a dot, dot, dot on both ends. We do need to express that this solution set extends infinitely in both directions. However, check out how there's symmetry here. Do you see how there's pi over 6 and minus pi over 6? There's 11 pi over 6 and minus 11 pi over 6. That perfect symmetry. That means there's a little shortcut you can use, where you can use the plus minus symbol to write two solutions in the form of one. In this case, you only need one dot dot, right? Because you actually almost folded the infinite list in half. So all four of these are totally valid ways of writing the solution set. Here's a second example. We're going to solve sine x equals minus 1 over 2. And again, we're going to look at the unit circle and ask ourselves, where does the sine function give a value of minus 1 over 2? And again, there are exactly two locations where that happens. So now the job is to write down every single angle that points in one of these two directions. So now in the basic unit circle, this corresponds to 7 pi over 6, and this corresponds to 11 pi over 6. So using indexing notation, I could write 7 pi over 6 plus 2 pi k, or 11 pi over 6 plus 2 pi k, where k is any integer. I could also write the infinite list, right? Substituting k equals 0, 1, -1, any numbers I wanted, I can generate this nice infinite list of numbers with an ellipsis on both sides. However, I cannot use plus or minus here. If I were to write plus or minus, that would be implying that positive pi over 6 is a solution to the equation, but that just isn't true. Or it would be implying that -7 pi over 6 is a solution, but that isn't true. So I just want to point out, you shouldn't assume that you always get to write plus minus when you're writing down your solutions. So here's some final tips. These two examples illustrate the process of undoing sine or cosine in order to isolate x, right? We're doing algebra equations. You want to isolate x. This is just one step. We're undoing a function which has been applied. Sine or cosine isn't multiplied. Therefore, you should never say divide by sine or divide by cosine. That is never, I guess, grammatically correct. This is a single step that you can take in solving sometimes multi-step problems. An order of operations is going to be very important. So for example, when we're solving 2 sine x plus 1 equals 0, there really is like a single correct order. You have to subtract 1 from both sides. Then you have to divide by 2 on both sides. Then it's time to isolate the x by undoing sine. You really can't begin by undoing sine. There's a specific order that really needs to be followed. And finally, it's tempting, but you're not allowed to factor constants in and out of the parentheses. That's what trig identities are for, and we're not doing those yet. So for example, sine of 2x is never going to be the same as 2 times sine of x. So anything that's inside the parentheses, you got to let that be and respect the order of operations.